Okay, now you can remember that previously we've talked about spanning sets, or the span of a set of vectors. And we've tried to find the span of column space, null space, row space, etc. So, and before we dealt with column vectors, so what we're going to do now is we're going to work with arbitrary vectors. And we're still going to have a space and find its span, but what we're going to ask is the question, given S, is S equal to W? All right, so you're given S and you're given W. You want to verify whether or not the span of S is equal to W. Okay, so let's see how this works. Okay. So here's a definition that seems quite familiar. If I have a subset S of a vector space V, then vector space could be a subspace. That's one possibility. Now, subset S of V is a spanning set if the span of S is equal to V. So this definition makes sense. Or we could just say this set S spans V. Okay, so here's one of our examples. We're going to do this different vector space, this vector space of polynomials. And we're going to ask the question the question I mentioned here above. Given a set S and a vector space W, is the span of S equal to the vector space W? All right, so we're going to use this subspace here that we looked at before, the subspace of all polynomials that have 2 as a root. Okay, and we're going to use this particular set of vectors. There's 1, 2, 3, 4 vectors in this set. Notice that one of them, this is not necessary, but one of them has degree 1, one has degree 2, one has degree 3, one has degree 4. And we're going to verify whether or not this set S actually spans this vector space W. Now, you should go through and verify that each one of these polynomials is in W. In other words, you should verify that each one of these polynomials has 2 as a root. Okay, so let's see. So now we've shown that S is in W, so that means the span of S must be inside of W, because W is closed under scalar multiplication and addition. Right, so now we want to show that every vector in W can be expressed as a linear combination of the vectors in S. Okay, so let's write down an arbitrary linear combination of the vectors in S that's expressed like this. Alpha 1 times the first, plus alpha 2 times the second, plus alpha 3 times the third, plus alpha 4 times the fourth. Now we want to write down an arbitrary vector that's in W. We want to write down an arbitrary polynomial that has 2 as a root. So what does it mean that 2 is a root of this polynomial? All right, so we've written down the most general polynomial of 4th order. What does it mean that 2 is a root? Well, it means that we can plug 2 in for x and we get 0 as a result. Okay, so that's what we've done here. Replace x with 2, and you get a times 2 to the 4th plus b times 2q plus c times 2 squared plus d times 2 plus e. So this polynomial, if 2 is a root, this polynomial must end up to be 0. All right, so this is a condition on the coefficients of every polynomial in W. Now note parenthetically that in fact this is the null space. The set of polynomials that satisfy this is the null space of A, where A is this simple row vector, 16, 8, 4, 2, 1. So what we're actually doing is we're verifying whether or not this set of polynomials is a spanning set for the null space of this matrix. Okay, so you can see that although we start out with polynomials, we're getting back to column vectors and matrices. All right. Well, let's go back to this arbitrary linear combination of the vectors in S. Now we can do our usual thing and rewrite this as a polynomial. Gather all of the x to the 4th terms, There's only one right here. Gather all of the x cubed terms. There's one here, and there's one here. Gather all of the x squared terms. There's one here, here, here. Yeah, gather all of the, and that gives you this one. Gather all of the x terms, gather all of the constant terms. So we've simply rearranged this linear combination to look like a nice polynomial. Now remember, we know what the conditions must hold, what conditions must hold on the coefficients of a polynomial. We know that 16 times the first coefficient plus 8 times the second plus 4 times the third plus 2 times the fourth plus 1 times the fifth must be equal to 0. Okay, so let's make that identification. We're going to say alpha 4 is our first coefficient. Our second coefficient is here. Our third coefficient is from here. Our fourth coefficient is from here. Our fifth coefficient is from here. And we also have the condition that 16, we also have the condition that 0 is equal to 16a plus 8b plus 6 plus 4c plus 2d plus e. All right, now what we have here, this looks kind of confusing, but what we actually have here is a system of equations with 8 variables: alpha 1, alpha 2, alpha 3, alpha 4, and a, b, c, d, e. I guess it's actually 9 variables. All right, now we saw this situation before when we were trying to express column space as a null space. And the way the book did it was to treat this last column as a column of variables and then row reduce. Now I just point out that you can actually, instead of doing it this way, you can row reduce a, you can write this entire system as a system of homogeneous equations. I could write this as alpha 4 minus a equals 0. This one's alpha 3 minus 8 alpha 4 minus b is equal to 0, and so on. I could write all of these as a homogeneous system of equations. There's 5 equations in 9 variables. So I could write down that big matrix and row reduce, and you'd get the same result as down here. Instead of writing this way, you'd get the fifth column would be 32, 24, 8, 1, 0. Sixth column would be 12, 6, 1, 0, 0, and so on. Okay, you can do this method and get the very same result. But the result is that, in fact, you can find a solution for no matter what a, b, c, d, you can find a solution to this system. Okay, so that means that you can always find the constants alpha 1 up through alpha 4 that give us these constants that satisfy the conditions that must be satisfied by a polynomial in W. So what that means is that the set S does span W. Okay. All right, so let's do another example in matrices. All right, let's consider the set of matrices that satisfy these two conditions. Now here we have 2 homogeneous conditions, so we can write this in this set Z, in fact, as a null space, and this 2 rows in the null space reflect the two linear dependence relations that are given that define the set Z. All right? So in order to figure out this space, we can row reduce this matrix. The null space of the row reduced matrix is the same as the null space of the original matrix, right? Because this is just a homogeneous system. All right, and then we have our 2 free variables and our 2 pivot variables. And see what this gives us here. This tells us that A plus, well, I can take them to the other side. A is equal to minus 3b plus d. That's what I get from this first equation. Second one, I get C is equal to minus 4d. Okay, so I can characterize the null space by these 2 equations. So that's how I can write the space Z. A is the set of matrices such that A is minus 3b plus d, C is equal to minus 4d. Okay, so in fact, this set Z is the span of these two vectors, these two matrices that we're considering as vectors. Okay, I'm going to skip this example, but he's using the very same techniques to get his conclusion. Okay, so same techniques that we've used before in a different context.